So there's one last type of reaction to talk about. It's actually the one you probably see most often. One you notice most often. So that last type is called combustion. So when you hear the word combustion, what do you think of? It's a fire, explosion, those types of things, right? Well, combustion means fire, okay? And to have a fire, when I was a scout, they taught me you needed 3 legs of a triangle. You had to have fuel, heat, and oxygen. So we're going to talk about a very specific kind of combustion, and that's combustion of and we're going to limit our fuel. Our fuel for combustion has got to be a compound that only has carbon, hydrogen, and it might have oxygen, it might not have oxygen. It's okay for it to have oxygen, it's okay not to have oxygen, but it's got to have carbon and hydrogen. And that compound with carbon, hydrogen, and maybe oxygen, that's our fuel. And we react that with oxygen, because to have a fire you have to have fuel and oxygen. No oxygen, the fire goes out. That's how fire blankets work. We stop the oxygen from getting to where it's burning. They smother it. And if we limit ourselves to these reactants, it always makes the same thing. It makes carbon dioxide and water. It makes carbon dioxide and water. That is complete combustion. That sounds pretty strange. See, we'll say, why do you say this? It says, I got fuel and oxygen, I'm going to make a fire. If I make a fire, I'm going to make carbon dioxide. That's not a problem. But I'm going to make water? Anybody ever seen water come out of a fire? Well, there's a chance you may have. Okay? Let me show you that water. I just want this because it's got a big surface area, we can see it. So I'm going to light some stuff on fire. Give myself a little fire. Okay, it's burning. And you can't see the water because it's a gas. But if I put this up, which is cool, see the condensation? If you've ever made macaroni and cheese on a gas stove, okay, you turn on the gas to heat the water, the outside of the pot gets wet. And the water's not leaking through the pot, it's the water from the gas stove burning the natural gas. So we can't see the water because it's a gas. But if I cool it off, we can see it show up on my beaker, right? As long as it stays cool, where it can condense. Ever see the water? I gotta be careful where I hold it, because it's hot on that side now. Okay? So fire makes water. It's kind of surprising. Okay? Okay, now sometimes things don't go well and you don't get complete combustion. You get incomplete combustion. And incomplete combustion happens when there's not enough oxygen around. If you don't have enough oxygen around, it still makes water, but it doesn't have enough oxygen to make CO2, so it only makes CO, carbon monoxide. So instead of making carbon dioxide, it makes carbon monoxide. And that's a problem because carbon monoxide is poisonous. And the way it poisons you is it hangs on to your red blood cells better than oxygen. So if you breathe air with carbon monoxide in it, the carbon monoxide grabs onto your red blood cells and never leaves. So those red blood cells can't pick up oxygen. So even though you're breathing, you're not getting any oxygen in, and you suffocate. Okay? That's how it kills you. Okay? Usually happens when things like your first time the heater turns up and birds have put a nest in your exhaust. It'll back up the fumes, and the fumes will back up into your house. And when they back up, they're gonna make it so there's not enough oxygen getting to the fire, so the fumes that back up are gonna have carbon monoxide. Okay? Or on really cold days, sometimes people say, "Ooh, it's cold outside, and my electricity's out, so I'm gonna bring the barbecue grill in." Light that up and heat up the house with the barbecue grill. Yeah. Tend to have fewer people in the house the next day when you do that. Okay? And if it's really incomplete, if you got really little oxygen, it makes just carbon and water. You've seen that if you lit a candle, that black stuff, the soot that comes out, that's the carbon. So when a candle first lights, it's not burning efficiently. And you get all that black soot, that's the carbon burning. But we don't have to figure anything out. We don't have to write special formula, don't have to do crisscross. All we got to do is say, hey, to have a fire, I need fuel, oxygen, and I'm going to make CO2 in water, CO in water, or C in water. That's it. There's no other figuring it out. So it's not like the other ones. Right? It's completely different. All the other ones, you got to figure out what you make on the other side. Here, you always make the same stuff. The most common mistake people make is you have to put plus O2. Even if the chemical has oxygen in it, you're going to have to add more oxygen to get it to burn. Okay? You always have fuel plus O2. So don't forget to put that O2 in there. So write the equation for the complete combustion of C4H10. C4H10 is butane, stuff in a lighter. Okay. So my fuel is C4H10. Everything else is the same all the time. I also have to have oxygen, and I make CO2 and H2O. So my plus sign back a little bit so I can put some numbers in. Okay, so I go to balance. 4 carbons, so I put a 4 in front of CO2. 10 hydrogens, so I put a 5 in front of water. That gives me 8 and 5, 13 oxygens. Can I get 13 oxygens on the other side? Nope, because one side's even, the other side's odd. So that means I'm going to go back and double that first one to make my odd numbers go away. So I now don't have 4 carbons, I've got 8. So I need 8 CO2s. I've got 20 hydrogens, so I need 10 waters. And now I've got 16 and 10 is 26 oxygens. And I can get 26 oxygens by having 13 O2s. So on these, leave oxygen till the end because it shows up twice. About half the time, you're going to have to put a 2 in front of it. What if it was incomplete combustion? Well, there's actually 2 possibilities. We'll do them both. If they don't specify, you could pick either one. Yeah. Okay, both you have butane. Both need oxygen to burn. Both are going to make water. But one of them is going to make CO and water. The other is going to make just C and water. carbon and water. Soot. Having balanced these lots of times, turns out all of these need a tube. I've done it before. Okay. So from my experience, I know these are going to need twos. You probably get there eventually. Okay, but so put a 2. Oh, come on, let me write. Not a big deal. 2, 2. That gives me 8 carbon monoxides and 8 carbons. That gives me 20 hydrogens, so I can put a 10 in front of water. 20 hydrogens, I can put a 10 in front of water. Notice that doesn't change the coefficients on the other side at all. What it changes is the oxygen. On that first one, I have 8 and 10 is 18, so it's 9 O2s. And the last one I have 10, so it's 5 O2s. Yeah.
Like, let's say this is on the test, we need to write both of them.
You could pick one. If I don't specify, pick one. Yeah. Unless I say write all the incomplete ones. If you don't, otherwise, I'm okay either way. Okay? Yeah. No, Isla? Because what do you need to have a fire? Fuel and oxygen. You always have to put plus O2 every single time. You can't have combustion without oxygen. So it's not going to tell you the oxygen. You have to put plus O2. Because to have a fire, you have to add oxygen. Okay? Yeah. Oh, yeah. Oh, but is it really difficult? What's difficult about it? This is much easier than everything else we've done. You memorize the 3 pieces. O2, CO2, H2O. You don't have to figure out what's on the other side. Okay? It's easier than what we've done before. Okay. What about the complete combustion of C6H12O6? So by saying the complete combustion of that, they're telling me that my fuel is C6H12O6. To have a fire, I can't have just fuel. I have to have fuel and oxygen. But say there's oxygen already. That oxygen's already taken care of. That oxygen's not going to cause the fire. We have to add more. It's complete combustion, so we always make CO2 plus H2O. So this part is the same for every complete combustion. Now I go to balance it. 6 carbon, so I put a 6 in front of CO2. 12 hydrogen, so I put a 6 in front of H2O. That gives me 12 and 6, 18 oxygens. So I can put a 9 in front of O2. No, I don't want to do that. Because that doesn't give me 18 oxygens. That gives me 24 oxygens. Don't forget those O's as well. So to have 18 oxygens on this side, 6 are already taken care of. I need 12 more. And that's the reaction you get. Anybody recognize this equation? Okay, well, last year you studied it backwards as photosynthesis. Carbon dioxide and water make oxygen and glucose. This is the opposite of photosynthesis. Glucose and oxygen make carbon dioxide and water. That was cellular respiration. That's where cells get their energy, is by doing this. Okay? So when they say you're burning calories, you're burning calories. That's the reaction. The sugar's the energy. You're going through the same thing as combustion. Okay? So when you lose weight, where does it go? You're on a diet. Want to lose some weight. Mass can't be created or destroyed. So that weight has to go someplace. Where does it go? I tell you, if you weigh yourself before you go to bed at night, and then you weigh yourself in the morning, you will be lighter in the morning. Everybody is. Why? Because you breathe. Where it goes, that's where you lose your weight. CO2 leaves. You exhale CO2. And that's where the weight goes. So when you exercise, you start breathing hard, exhaling more CO2. You're actually losing the weight. It's actually leaving your body in your breath. Okay? So when you lose weight, that's where you lose it. Okay, just one last one because it's the mistake people make most often. It's a really simple one, and I will just do the one for CO this time. Because with incomplete combustion, well, first of all, it says combustion. Combustion always has two reactants, fuel and oxygen. I have to put plus oxygen every time. And it said incomplete. This time I just want to do the carbon monoxide and water. There's 2 carbons, so I put a 2 next to carbon monoxide. There's 6 hydrogens, so I put a 3 next to water. That gives me 2 oxygens and 3 oxygens on my right side. That's 5 oxygens. On my left side, I got 1 oxygen already spoken for. So I need 4 more. Can I get 4 more? Just had to put a 2 there. And now that's 5 oxygens over here, 5 oxygens over here. 2 carbons on both sides, 12 hydrogens on both sides. So the only thing is if there's no here, don't forget to go back and count it when you put the number in front of O2. That's the mistake people can make. And just one last thing before I set you back. A few of you have written this already, but I just want to make sure everybody's online. If it's not combustion, because combustion plus O2 makes CO2 plus water, right? So how do we recognize which type it is? Because that's the first step in predicting what it's going to do. Because if you can label it as decomposition, you know that it's got to decompose, fall apart. I should get more pieces. Once you can label what kind it is, you know what to do with the pieces. So you got to look at the reactants because you're not going to predict the products if I already tell you what they are. And rather than writing out a whole bunch of stuff, I'm going to come up with a complicated shorthand system. Here's my complicated shorthand system. I'm going to let E stand for element and C stand for compound. Notice that complicated substitution there? Because if your reactants are 2 elements, reactants are 2 elements, it's a combination reaction. Because that's the only way 2 elements can change. Is elements, they're by themselves. If you got 2 things by themselves, the only way they can change is not be by themselves anymore. Does that seem reasonable? So you put them together, do the crisscross. Decomposition. It's going to decompose. To fall apart, you start off with 1 piece and end up with more pieces. So you're going to start off with something that can fall apart, a compound. It's going to decompose into its elements. On that one, you just have to worry about do those elements get a little 2 or not. If you've got an element and a compound, something by itself and something with a partner, that's a situation for single replacement, where that element can replace another element. Right? And if you got 2 compounds, that would be double replacement, because they got 2 places where they can switch partners.